Hi, we are presenting for phase 2 of our deep learning project Improving Hand Anatomy for PixArt-alpha. I am Arpita and I'll start by giving a quick overview of the base paper. So modern text to image models like Stable Diffusion can generate very high quality images, but the problem is training these models is extremely expensive. It requires millions of GPU hours, massive data sets and a lot of money. Because of this, most research groups can't afford to train or experiment with such models from scratch. PixArt-alpha tries to solve this problem by asking a simple question: can we achieve similar image quality but with much less compute? The main idea behind PixArt-alpha is to break the training process into three small, more manageable stages instead of doing everything at once. In the first stage, the model is trained on ImageNet using only class labels. This helps it learn basic visual features like shape, textures, and colors without needing expensive text image pairs. In the second stage, the model is fine tuned using high quality image caption pairs. This is where it learns how to connect text with images, basically, how to follow instructions from language. And in the third stage, the model is trained at higher resolution using human preference data. This step improves the visual quality and makes the output more realistic and appealing. So instead of one huge training process, we have three smaller focus stages, and that's what makes the whole approach much more efficient. Now let's look at the architecture. PixArt-alpha uses something called a diffusion transformer. Unlike traditional models that uses UNet, this one is fully transformer based and works in a compressed image space. First, the input text is processed using a T5 encoder. This converts the text into rich feature representation that capture the meaning of each word. At the same time, images are compressed using a VAE into a smaller latent space. This makes the computation faster while still keeping the important visual details. Then come the core transformer blocks. These use self attention to understand the structure of the image and cross attention to connect the image with the text. This is what allows the model to generate images that match the given description. Finally, additional information like the diffusion timestamp and the text features are added using adaptive layer norm. This helps keep the training stable and improves the final image quality. Overall, this architecture is both powerful and efficient. And because of this design, PixArt-alpha is able to achieve strong performance. For example, a good FID score on COCO while using only about 10% of the compute required by models like Stable Diffusion. So overall, PixArt-alpha gives us a compute efficient and modular model which is also very suitable for fine tuning. And that's exactly what we build on in our project. Now I'll hand it over to Prajna who will walk you through our approach.
So while PixArt-alpha is great at general image generation, like most diffusion models, it consistently fails at hands, producing fused fingers, wrong finger counts, and distorted geometry. Our goal was to fix this through targeted LoRA fine tuning. So we worked with two public hand datasets. The 11K hand dataset contains about 11,000 images with clean backgrounds and consistent lighting and easier distribution. Freehand has 130,000 images captured in the wild with occlusion, perspective distortion, and cluttered backgrounds, which is much harder. We ran three dataset configurations, all keeping 3000 total images to isolate the effect of composition. Config A was 2000 freehand plus 1011K, config B was 500 freehand plus 2511K, and config C was 11K only. So since raw images lack the precise captions needed to guide hand generation, we used Lava 7b to generate dense anatomical captions for every image, prompting to describe finger count, separation, knuckle visibility, palm orientation, texture, and lighting. So rather than retraining PixArt from scratch, we used LoRA, low rank adaptation, to efficiently adapt the model. The idea is to inject small trainable low rank matrices into the attention layers of the diffusion transformer, specifically the QKV and output projections, while keeping the VAE and T5 encoder completely frozen. So we set LoRa rank R equals to 16 and alpha equals to 32, following the standard rule alpha is equal to 2R. So this introduces very few additional parameters, making training feasible on a single GPU. For hyperparameters, we used Optuna initially to explore ranges, but found that it sometimes suggested unstable rank alpha combination, So we used Optuna for range guidance only and manually selected clean final values. Learning rate 5 into 10 power minus 6, consigned scheduler with 200 warm up steps, batch size 2, gradient accumulation of 4, trained for 15 epochs at a resolution of 512. We evaluated using FID, which implies that lower is better, and T2I bench for compositional reasoning. So on the custom hand data set, the basic PixArt-alpha FID was 126.73, and after just 500 steps of LoRA training, it dropped to 116.41. The final merged model brought it down to 109.61, which is quite a meaningful improvement. T2I bench code stayed flat across all model variants, which makes sense. We were fine tuning specifically for hand anatomy, not general compositionality. General image quality on Coco prompts was preserved. The 11K configuration outperformed the mixed configs because it is cleaner. Consistent distribution let the LoRa adapter focus its limited RAM budget on finger count and geometry rather than dealing with background variation. Increasing the proportion of 11K images consistently improved results across configs A, B, and C. I'll now hand over to Sreenitya for the live demo.
I'll now show you the live demo running on our radio interface. Here we have 4 different models, base, 2 checkpoints, and the merged model, which is a combination of the 2 different checkpoints. So let's start with a general prompt to show that the model hasn't forgotten how to generate non-hand context. I'll type a person sitting on a park bench reading a book, and the setting will be golden hour lighting. You can see that the quality is preserved. The model still handles general scenes well. This is important because one risk of fine tuning is catastrophic forgetting, where the model degrades on general prompts. The FID on Coco still confirms that this is not happening. Now let's test what we actually fine tuned it for. I'll use a hand specific prompt. For example, a close up photo of an open human hand with 5 clearly spaced fingers. Clearly, let's use separated. And the palm facing forward. And the lighting shall be natural. Compare this to the base model would produce. It would produce fused fingers, sometimes a 6th finger, and distorted knuckles. Our merged model produces clearly separated digits and anatomically plausible geometry. So now let's try another. Let's try 2 hands together, like they are clasped together and fingers interlocked, and the skin tone shall be warm. These 2 hand prompts are particularly challenging for diffusion models. You can see the improvement in structure here. Now let us look at our 1B training logs. We have evaluated the model on 10 fixed hand prompts across multiple checkpoints. The sample image grids are shown on the screen. The earlier checkpoints struggled. The outputs were noisy and unrecognizable and heavily malformed. But as the training progressed, we can visually see the model correcting itself. There is better finger separation, cleaner geometry, and more anatomically plausible hands. Based on this visual sweep across all checkpoints, we identified 2 that consistently produce the best results. Rather than just picking one, we merged them, and that merged model is our final output. This visual alongside our FID scores gave us confidence that the fine tuning worked. To wrap up, here's a clearer summary of everything we've done. A direct visual comparison across all 4 model stages on the same set of hand prompts. Starting with the base PixArt-alpha model, you can immediately see why we chose this problem. Claw-like fingers and completely wrong finger counts, distorted palm geometry. Some of these don't even look like hands anymore. This is the classic hand failure mode that diffusion models are notorious for, and it's consistent across every single sample in the base model. Now, if we look at checkpoint 500, the LoRa fine tuning on 3000 curated images, the difference is clearly visible. The hands are recognizable, fingers are separated, and the proportions are natural. The backgrounds have also become cleaner and more consistent. This tells us that LoRa adapters started learning the right signal very early in training. Checkpoint final. This refines it further. We can see more realistic skin texture, better knuckle definition, and correct palm orientation over a variety of poses: open palm, raised hand, different angles. The model has clearly internalized what a hand is supposed to look like and not just memorized a single view of it. The diversity across prompts holds up. And finally, the merged model, where we fold the LoRa weights directly into the base transformer. This is our best results: anatomically correct hands across varied prompts, lighting conditions, and backgrounds. 5 fingers, proper separation, natural proportions, consistently. What we are looking for is the outcome of clean training data, dense lava generated anatomical captions, and a stable LoRa configuration. 3000 images with no full training, only targeted adaptation. That's our project. The code, model weights, and evaluation pipeline are all on GitHub. Thank you.